Today we're going to be looking at scientific notation. And scientific notation has a specific form. It is going to look like A times 10 to the B power. And each part of this has specifications. So the number in front of the multiply that we're going to refer to as A, its value has to be between 1 and 10, but it cannot equal 1 and it cannot equal 10. So it has to be some value in between those. Then for multiplication, you have to use an X. Don't use the dot. In proper form, it's an X. Come on, Peter. Then for here, for scientific notation, you're always going to take a value times a base 10. So this is always going to be base 10. And then last but not least, we're going to talk about the exponent up above. So this guy right here for B. There's no specifications on what it can and can't be, but we're going to talk about what type of number it produces. If the exponent on base 10 is a positive number, then you are taking your A value times a 10 to a positive power. So you have 10 to the first, which is 10. 10 squared is 100. 10 cubed is 1,000. If the exponent on 10 is positive, that creates a large number in what we call standard form. Standard form is just not scientific notation form. And conversely, if that exponent is negative, remember that negative exponents create fractions. So that's going to create a very small number in standard form. Okay, so let's get some practice on determining what the proper notation is and how to make adjustments if needed. So for these three, all we're going to do is decide if they are written in proper scientific notation or not and explain. And we're going to take a look at number 1, 0.23 times 10 to the negative third. This one is not in scientific notation because of this A value. Remember, the A value has to be between 1 and 10, but cannot equal 1 and cannot equal 10. So 0.23 is less than 1, which doesn't qualify as proper scientific notation. Everything else about it's fine, just not the A value. So look at number 2. My A value is between 1 and 10. I have the X, I have base 10, and I have an exponent on base 10. So this one is in proper scientific notation. And in number 3, at first glance, we go, well, 9.3 is between 1 and 10. That's good. We use the X. But then right here is the issue. 100 is not, this is base 100, not base 10. We could make adjustments, which we'll see here in a little bit. But as it is, this one is not in scientific notation because it doesn't use base 10. Okay, so let's take a look at some examples about turning these into scientific notation. So these are all numbers in standard form. What would they look like in scientific notation? So I'm needing to convert this into something times 10 to some power. Now recall that that A value has to be between 1 and 10, but not equal to 1 and not equal to 10. So right now my decimal is at the very end of this very large number. And I have to figure out, well, how many places do I need to move it until it becomes a number between 1 and 10? And that would be right here between the 1 and the 4. So I would have 1.43 times 10 to, and the power of 10 will be how many places you had to move your decimal. And in this case, from where it began at the end of the number to where we moved it to in between the 1 and the 4, it has moved 9 places. We know that 9 is a positive as well because my standard form number is a very large number. And I'm only going to be able to turn a 1.43 into a very large number if I multiply it by a base 10 with a positive exponent. Okay, on 5, we're going to set it up kind of the same idea. Again, for my A value, I need to move this decimal until I get to be a number between 1 and 10, and that is looking like a 3.2. Now, I can already tell from the beginning of this that my standard form is a very, very small number, right? It says a decimal with a lot of digits. So I know that this exponent has to be a negative. Now, how many spaces did we move? Well, we moved 5. So this exponent would be a negative 5. Okay, if you are watching this at home, try this last one on your own and then hit play to check your answer. If I move my decimal in on this one, I'm going to end up at 6.78. And then how many places did I move it? I had to move it 5 places. But this ends up staying a positive 5 because in standard form, this was a pretty large number. I didn't create a small number, which would make the exponent negative. Okay, now let's reverse this process. I'm going to take a number in scientific notation and I'm going to rewrite it into standard form. So to do this, I'm going to write down my 5.5. I know I'm going to have to move my decimal 6 places, but I have to figure out what direction. Well, if that is a positive 6, 5.5 is going to end up becoming a very large number, which means I'm going to have to move my decimal to the right to start making it that large number. And I need to move it right 6 places. So here's 1, 2, 3, 4, 5, 6. And in all of those empty spaces, I'm going to end up with zeros. So I have 5, 5, and then 1, 2, 3, 4, 5 zeros. And then place your commas where they would go. So right here would be my answer in standard form. Let's take a look at 8. I start with 3.1. I need to move the decimal 3 places, but because this exponent is negative, I'm going to make 3.1 a even smaller number, which would mean I need to move to the left 3 places. So I would start with my decimal, and then I have 2 zeros, then the 3, and then the 1. On number 9, if you're at home, pause your video and try this on your own, and then you can check your answer when you hit play again. Okay, I have to move 7 places, and that's a positive 7, so I'll be going to the right in order to make this number a large number. So I have 5, 2, 3, followed by, I think I'm 1, 2, 3, 4, 5, 6. I am 1 loop short. Here we go. Then I would have 5 zeros. And that right there would be my value in standard form. Okay. Now we're going to apply operations to our scientific notation. And the biggest thing that you have to remember is even though this seems like a binomial, that it seems like there's two numbers in there, that really is only one number. 3.2 times 10 to the negative fourth, right? That's 3.2, but move your decimal 4 places to the left. Then multiply it by 5. But we actually don't even have to do that. We can recognize that I am just multiplying 5 times that value. And so if I take 5 times the 3.2, it's still going to be times 10 to the negative fourth. So 5 times 3.2 is 16. And if we stopped here, we would be close, but we are not in proper notation. This is not proper scientific notation because this right here is larger than 10. So to move the decimal in order to make it proper notation, this would be a 1.6. But if I move the decimal, that is going to affect the exponent. And the best way that I know to think about this is if I think about that first answer, it was a 16 with a decimal right here. But it's times 10 to the negative fourth power, so I would move left 4 spaces, and that's 0.0016. So if I have now moved my decimal to start in between the 1 and the 6, how many places do I have to move the decimal for it to be the same value? That would be 1, 2, 3. So the exponent on this new form would be a negative 3. I have to move that decimal one less place when my A value turns into a 1.6 than I did when it was a 16. Okay, on 11, it's a similar idea, but I have two scientific notations times each other. But it's just one number times the other. This is only two numbers that we're multiplying together technically. And to evaluate this, you multiply your two A values together. So 3 times 2 is 6. And you multiply your base 10s together and use your laws of exponents to know that 10 to the negative 6 times 10 to the 12th is 10 to the 6th. Double check, is this proper form? And it is. 6 is in between 1 and 10, and I have it times a power of 10, so we don't have to make any adjustments on this one. It's ready to go as is. Okay, 12 is going to be a lot like 11, but you've got to remember what squared means. That means taking the number times itself. Now we're going to multiply just like we did in 11. 4 times 4 is 16. Times 10 to the, 10 cubed times 10 cubed is 10 to the 6th. But once again, I'm not quite in proper form, right? 16 is bigger than 10. So I need to change this to a 1.6. And when I do that, that's going to affect this exponent here. So either visualize or think about that 16 times 10 to the negative, or 10 to the 6th means I started with my decimal point here, and I would have to move it 6 places to the right. So I would have 6 zeros to follow. If I needed to start my decimal in between the 1 and the 6, well, to create that same standard form number, I would have had an additional place value to move. So this becomes 1.6 times 10 to the 7th in order to be an equivalent form, but in proper scientific notation. Okay, these are the same idea. On 13, these are cubed, right? So you want to think about, I'm going to cube 1.4 and I'm going to cube 10 to the negative 8th. And honestly, 1.4 cubed, I got a calculator out, right? 1.4 times itself 3 times is a 2.744. And then use your laws of exponents to recognize 10 to the negative 8th to the third becomes 10 to the negative 24th. And this one's pretty nice because we do not have to make adjustments. A is in between 1 and 10, and you're already base 10, so you're good to go there. Now we have division. Just like multiplication, you're going to divide each part. You're going to take that 3.6 and divide it by a 1.5, and that's going to be times 10 to the 7th divided by 10 cubed. Again, I would grab a calculator to do 3.6 divided by 1.5, and I got a 2.4 times 10 to the, well, division, subtract your exponents, and that would be to the 4th. And this is another nice one that we don't need to make adjustments for since A is already in between 1 and 10. Okay, one more, and I'm going to do a little bit less work to show on this one, but I'm going to divide these and I'm going to divide these. 4.5 divided by 5 is 0.9. 10 to the negative 6th divided by 10 to the negative 2nd is 10 to the negative 4th. Because A is not bigger than 1, I have to make an adjustment. So I would need to move the decimal, so where this is just a 9, which means the exponent also adjusts. If I think about that number originally, I would have to move it, the decimal, 4 places left. If I want to make that same number equivalent to if I started on the right hand of the 9, I would have one more loop to go. So this would have to be negative 5. Okay, we have 2 more of these operations to look at, and it's bringing back in radicals. Again, you're just going to take the radical of each piece. So I've got the square root of 36 times the square root of 10 to the 10th. Well, the square root of 36 is 6. And we've talked about it previously, but it's been quite a while. You need to recognize that a square root is the same thing as a 1/2 power. So here, once again, you have the power to a power rule that says you multiply those exponents. So this would become 6 times 10 to the 5th. And again, no adjustments needed because that 6 is already in between 1 and 10. Same idea goes for a cube root. We haven't worked with cubes a lot, but for the cubed root of 8, you have to ask yourself what number times itself 3 times is 8, and that is a 2. Then for a cube root, that would be a 1/3 power. So again, apply your power to a power property, and you're going to get that that's just 10 squared. So there it is. That's it. All right, now let's look at some applications of scientific notation. Like, when would these potentially be used? So the diameter of a golf ball is 4.27 times 10 to the 1st millimeters. The diameter of the Earth is 1.27 times 10 to the 10th excuse me, millimeters. How many times bigger is the diameter of the Earth than the diameter of the golf ball? There are a few ways to set this up, and the one that makes sense to me is, well, I'm going to take the golf ball, so maybe if it lets me, right? 4.27 times 10 to the 1st. And I'm going to multiply it by my unknown. Like, what do I need to multiply that golf ball by to get the diameter of the Earth? Now, what you use for this unknown is up to you. I'm going to use a capital X, a bigger X, so that I don't confuse that with my multiplication sign in scientific notation. But you can really use a Y, you can use anything else. But the goal is to get that unknown alone. So I'm going to divide by the 4.27 times 10 to the first on both sides. So that gets it to cancel on the left. And I'm left with, again, just like we did earlier, I'm going to use a calculator for what is 1.27 divided by 4.27. And I got 0.2974. I had to round a little bit. And then it would be times 10 to the 9th. But I do need to make an adjustment. This isn't proper scientific notation. I need to move that decimal to actually be between the 2 and the 9. In doing that, again, you can write it out or you can think about it. That means that is one less space for me to have to move my decimal to be the same number in standard form. So to answer our questions, how many times bigger is the diameter of the Earth than the diameter of the golf ball? It would be 2.974 times 10 to the 8th times larger. And we don't have unit. Well, you said millimeters, so let's add that in there. Millimeters. Millimeters wouldn't attach here. It would be times larger. Okay, we have one more of these that we're going to do together, just to show you that it might look overwhelming when you first read it, but they really aren't terrible questions at all. And this would be a good example of one that's intimidating when we read it, but then hopefully we find that it really isn't that bad. The strength of the electrical field produced by an electrical dipole is E equals 9 times 10 to the 9th times the quotient of Q squared and R cubed, where Q is the charge and R is the distance from the charge. What is the electrical field strength? So this is what we're trying to find. That's E. If the distance of R equals 10 to the negative third meters produced by charges with a strength of Q equals 10 to the negative sixth. I have R and I have Q. I just need to plug all that in to this equation that they gave me. I don't know E, that's what it asked me to find. I know that I get E by taking 9 times 10 to the 9th times Q squared. Well, Q is 10 to the negative sixth. And I got to square that. Over R cubed, R is 10 to the negative third, and I'm going to cube that. So let's start cleaning it up. I'm going to focus on this second parenthesis set. I'm going to start simplifying it by order of operations. 10 to the negative sixth squared becomes 10 to the negative 12th. 10 to the negative third cubed becomes 10 to the negative 9th. Okay. Now I'm going to keep simplifying within that second set of parentheses. And I'm going to say, okay, well, 10 to the negative 12th divided by 10 to the negative 9th is 10 to the negative third. And when I multiply scientific notation, I know that I'm going to only multiply the like pieces. So the 9 is going to stay the same. And I just have to do 10 to the 9th times 10 to the negative third, which gives me 10 to the 6th. So that's already in scientific notation, so I don't have to adjust this one. And then the answer didn't give us measurements, so you can, on this one, you can add in as it's just units. So the electrical field strength is 9 times 10 to the 6th power units. Okay, that is scientific notation.